Let's take a look at transformations of functions and see how the transformation affects the graph. So before we do that though, you need to understand that there's some different types of transformations. These first two, shifting and reflecting, those are referred to as rigid transformations. They're just moving our graph. They're not changing the size or shape of our graph. On the other hand, the stretching transformations, those are referred to as non-rigid because the size and or shape might change. Before we get into examples of those though, there are some common functions that you should be aware of and know what the graphs look like right away. And so these 6 parent functions show up a lot in our transformation examples. First of all, everybody knows what y equal x looks like, right? Slope of 1, y-intercept of 0, looks like that. There should be arrows on the ends. It goes on forever and ever. The domain is all real numbers. The range is all real numbers. Second one is the square root of x. We should know what that looks like. Notice the domain, x has to be greater than or equal to 0. And then the range, y is going to be greater than or equal to 0. Our parabola, the domain is all real numbers. You can have any number plugged in for x, but your outputs are going to be non-negative. So your range is going to be 0 to infinity, including 0. The other 3 you should be familiar with. Absolute value of x. Usually students remember that's a v. Here the domain is just like the parabola, all real numbers, but the range, just like the parabola, is greater than or equal to 0. So 0 to infinity, including 0. Y equal x cubed shows up once in a while. Looks like that. The domain and range are both all real numbers, or negative infinity to infinity. And then the last graph, we'll talk more about rational functions later on in the course, but you should know what 1 over x looks like. And it's got a vertical asymptote at x equals 0, which is the y-axis, and it has a horizontal asymptote at y equals 0, which is the x-axis. So the domain is all real numbers except 0, and the range is also all real numbers except 0. So you should be familiar with these 6 functions right off the bat. Okay, so let's get into transformations. Let's talk about vertical and horizontal shifts of graphs. So let's look at this example here. We've got h of x equals x minus 3 quantity squared. The parent function for this is just y equal x squared. So I'm going to start with that. I'm going to graph its parent function. So I have x and I have the parabola y equal x squared. And I'll just pick some values. 0, when I square 1 I get 1, 2 squared is 4, 3 squared is 9, etc. Throw in some negative values as well. Negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9. All right, so if I go ahead and plot those points, we got 1, 2 goes up to 4, 3 goes way up there to 9, and then negative 1, negative 2, negative 3. Okay, so we're familiar with this graph. That's our parent graph. So now we want to graph this new function, h of x, and see what happens when we plot these points. So I'm going to do x minus 3 quantity squared. So when x is 0, I get negative 3, quantity squared gives me a 9. When I plug in 1 for x, so just to make sure you're following where I'm looking, these are my inputs, and then these are going to be my outputs. So I'm plugging in 1 for the x, 1 minus 3 is negative 2, squared is a positive 4. When I plug in 2 for x, 2 minus 3 is negative 1, square that I get 1. When I plug in 3 for x, 3 minus 3 is 0, squared is 0. Now when I plug in negative 1 for x, negative 1 minus 3 is negative 4, and I square that and I get 16. So let me plot the first few here. So now remember, I'm plotting the first column, those are my inputs, And then the third column, these are my outputs for this new function h of x. So 0, and I output a 9. When I input a 1, I output a 4. When I input a 2, I output a 1. And when I input a 3, I output a 0. And maybe I should change some values in my table instead of these negative values. Let's keep going. And how about I plug in 4, 5, and 6. Let's see, I plug in a 4, 4 minus 3 is 1, squared is 1. Plug in a 5, 5 minus 3 is 2, squared is 4. Plug in a 6, 6 minus 3 is 3, squared is 9. Okay. And these were values for the other ones. All right, so let's plot those. 4, 1, 5, 4, and then 6, and I jump way up here. So look what happened to my graph. You probably already know what I'm going to say before I say it, just by looking at this visually. You can see that every point on the original parent function got moved over 3 units to the right. This point here, 3 units to the right. This point here, 3 to the right. This point here, 3 to the right. So my original graph, y equal x squared, by doing x minus 3, moves everything 3 units to the right. Because what used to happen when x was 0, now is going to happen when x is 3. When x is 0, I got 0. Now when x is 3, my new function gives me 0. So a lot of times students think, oh, because it's a minus 3, it's going to shift it 3 this way to the left. But it actually is moving it 3 to the right. Because I need to increase my x values by 3 to get the same output as I did before. So instead of a 1 to get a 1, I need to plug in a 4 to get a 1. All right, let's look at what happens with the square root of x plus 2. So I'm going to make a table, and my parent function is the square root of x. 0, square root of 0, 1, square root of 1, 4, square root of 4, 9, square root of 9. So we get these familiar points. And 9 should be over here, gives me 3. All right, so there's your parent function. That's just y equal to the square root of x. Now, our new function g of x is the square root of x and then plus 2. So notice what's going on here. For my inputs, I still have to take the square root, just like I did here. So I'm going to get all these answers, and then for each of those answers, I have to add 2. So essentially, I'm just adding 2 to the outputs of my original function. So this is going to be a 2, this is going to be a 3, this is going to be a 4, and this is going to be a 5. So now I'm plotting the point 0 input, 2 is the output. 1 is an input, gives me 3 as an output. So let's plot those. 0, 2. 1 gives me a 3. 4 is going to give me a 4. 9 is going to give me a 5. So you can see that this doesn't change the size or shape of my original parent graph. All it did was shifted each of these points up 2 units. And that's because I'm adding 2 after my original parent function. That's different than what happened in the first one. I wasn't subtracting 3 after the x squared. I wasn't doing x squared and then minus 3. If that were the case, then all these I just subtract 3 from, and then that would pull all these points 3 units down, as opposed to 3 units that way. So let's summarize what we've found out from this. If c is a positive real number, and I have my parent function y equal f of x, then if my new function is the original function plus a constant, that's just going to shift everything upward that many units, c units. So that was this example here. Plus 2 just moved everything up 2. My output column, I added 2 to it. So that shifts everything upwards vertically. And if I did a minus, like if I did a minus 2 on that square root, it would have pulled everything 2 lower, so that would be a shift vertically downward. So adding or subtracting a number after the original function is going to be a vertical shift. Adding will shift it upwards, subtracting will shift it downward. If I'm adding or subtracting numbers on the inside with the x value, then that's going to be a horizontal shift, like the first example. If I'm subtracting a number, that's going to shift it to the right, like we did there. It shifted it 3 to the right. And if I'm adding a number, it's going to be a horizontal shift to the left. So this is the one that usually messes students up. This is pretty easy. Plus a constant, that's just up, minus is down. But here it's the opposite direction. So a minus is horizontally shifting to the right, and a plus horizontally shifting to the left. And all you really need to do is an example or two, and then you'll remember that.